Hello and welcome to the Charles Law Balloon Lab. Introduction. Matter exists in three states: solid, liquid, and gas. When an element or compound absorbs a great deal of heat energy, it will turn into a gas. Gases are characterized by a high degree of disorder, entropy, random particle movement, and they exert a pressure on their container. They do not have a definite shape or volume. Instead, they take the shape of their container. Hydrogen and helium are the most ideal gases. Gases are most happy when given freedom, low pressure. Throughout history, chemists have explored the relationship between three variables that dictate the behavior of a gas: pressure, volume, and temperature. Jacques Charles, a French chemist, studied how temperature affected how oxygen, O2, nitrogen, N2, hydrogen, H2, carbon dioxide, CO2, and air, a homogeneous mixture of many gases, behave. Today we'll be performing the Charles Law Balloon Lab. So the materials we're going to use: the balloon, a hot plate, I'm not going to use a string or tongs, we will use a tape measure, ice, a beaker, a bucket, and a calculator. So the first thing we're going to do is take our balloon, I chose orange, and we're going to blow it up. So the procedure says I suggest a smallish balloon. That's your call. So one breath of air we'll put in there. We'll see what size it is. Looks good to me. So now we have to measure the circumference of the room temperature balloon, and we will do that in centimeters. So one good trick, once we wrap the measuring tape around the balloon, is to mark the path that we took. So as we do this lab, we're always going to take the same path. So it doesn't have to be perfect, doesn't have to be the perfect circumference, but as long as we keep taking the circumference in the same spot. So I'm going to draw little lines to show where I have the tape measure on this side, and then also on this side. So as I read, try to make it as tight as you can without stretching the balloon, squeezing the balloon. It looks like our circumference is 56.4. centimeters. So room temperature, 56.4 centimeters. So what I did here on the balloon, I have like an equal sign. That's the path that the tape measure went through, and they're on both sides. So what we're going to do now is we're going to put it in the cold ice bucket. We have ice in the bucket. We put it in here. We'll rotate every 30 seconds. So for about 5 minutes, we'll have it in there. While we wait for the balloon to get cold, we can do the calculations for the room temperature balloon. So the first thing we are going to do, 56.4, we're going to divide the circumference by pi. So find the pi button, 3.14. And on this calculator, it's right here. So 56.4 divided by pi is going to give us a very long number, 17.95267758. That's okay, we'll do significant figures at the very end. 30 seconds has passed, so we'll flip the balloon over, try to cool it down on all ends for about 5 minutes. The radius, so we take the diameter, do not clear out your calculator, just divide by 2. Once again, you should have a very, very long number, 8.97633.879 centimeters. And then for the volume, this is tricky. So what I would do is I would work backwards. We have the radius. We have radius. I would raise that number to the third power in my calculator, hit enter, times pi, hit enter. So now I have 2,272.205358. When I'm not done, I have to do times 4/3, so times 4 divided by 3. So the volume of my balloon is 3029.60714 cubic centimeters. We'll round to 3 significant figures. First, let's rotate the balloon. Oh, it's going to get away. 3 significant figures, 1, 2, 3, 9, higher than 5, so our final answer here is 3030 cubic centimeters for the room temperature balloon. So about 2 minutes have passed on the balloon. You want to rotate the balloon every 30 seconds or so to make sure the cold is getting all sides. You don't want to touch it with your hands, so maybe I could go like this. I could touch it with the plastic expo marker and kind of force it a little bit into the cold ice. I don't want to touch it directly because my body heat is going to affect the results. We're trying to see what effect temperature has on the volume of the balloon. So here we have cold ice. We do not want our body heat to affect our results. So rotate it again. By holding the expo marker and having that touch the balloon, my body heat's not going directly from my hand to the balloon. Hopefully the marker is absorbing some of my body heat. Remember, this marker is made of plastic. Plastic is not a good conductor. Plastic has a high specific heat, so it is a good insulator. Plastic is a very good insulator. So it will not transfer my heat, my body heat, to the balloon. It's about time we'll rotate it again. Here we have a hot water bath. I took a 1,000 milliliter beaker, filled it about halfway with water, put it on the hot plate, and cranked the hot plate all the way up. While we're getting the cold temperature, we'll wait for the hot plate to boil the water in the beaker. The balloon looks a little misshapen, so I'm going to go back on this side. You know what, let's go this side. So I want to do this for 5 minutes. The longer, the better. But try to keep it even between the cold and the hot. You want to keep that as a variable that does not change and control the amount of time that the temperature is being changed. 30 seconds. Let's go to the side, actually. Got 15 seconds left. So remember, Charles' law is a direct relationship. Volume and temperature are directly related. About 5 seconds. Okay, so let's record the new circumference. You want to do it fast because we just took it off the ice. We want to see if our numbers changed. Go along the same path. Oh, we're off a little bit. And our numbers changed oh so slightly. It looks like we are at 55.7. Cold balloon, 55.7 centimeters for our diameter. Now we'll do the same thing. We'll put the balloon this time on the hot water bath, the beaker with the hot water. It's not boiling yet, but that's okay. So we'll put it on the hot water bath, and then it should start to boil as time goes on. So every 30 seconds, we will rotate it. If we remember, we'll just do our best. So we're at 10 seconds in already. The cold so far looked like it went down. Now we're going to see what happens when we put the balloon on the hot water bath. 5 seconds we'll rotate it, and then we'll start doing calculations. Okay. All right, so do the same thing again. We have 55.7. The trick here is never clear out your calculator. 55.7 divided by pi, 3.14. If you have a pi button on your calculator, please hit the pi button on your calculator. So if we do that, we get, let's rotate. Our circumference is, our diameter is 17.72986.066 centimeters. Continuing on, divide by 2. So we're just cutting that number in half. And before we go any further, let's rotate the balloon. Doing a little bit better this time rotating the balloon, that's okay. We have 8.86493033 centimeters. And then the tricky one, raise it to the third power. I get 696.6681891. Of course, let's rotate. Now we have to multiply by pi times pi. I get 2,188.647665 times 4 divided by 3. So we get 2918.196886. Let's rotate our balloon. And if we round to significant figures, once again, 3 significant figures, 1, 2, 3, 8, higher than 5. So our final answer is 2920 cubic centimeters. So we can see that from room temperature to cold, the balloon decreased in volume. Now it's time to rotate again. We got 2 more minutes. We can see the water is boiling. So that means the water is roughly 100 degrees Celsius. The temperature will not change during the phase change. We learned about that during thermochemistry. If you look carefully, you can see the balloon. It looks like it's starting to expand a little bit. And then 30 seconds, let's rotate. A little bit more than a quarter turn. Once again, I do not want to touch it. I want my body heat to affect the results. In this case, remember, heat flows from hot to cold. So potentially, if the hot water is at 100 degrees Celsius and my body is about 38 degrees Celsius, the hot air will go from the balloon, if it's hot enough, to me. Another 30 seconds has passed, we'll rotate. Another minute left. The reason why you want to fill the balloon up too much is you don't want it to pop during this experiment. See the balloon moving a little bit? All right, last 30 seconds. Definitely have a rolling boil inside of the beaker. I'll get the tape measure ready. So as soon as we are done, we can measure the circumference. 10 seconds. See a little condensation on the balloon. 2 seconds. All right, let's pull it off. Let's go right away before it cools down. Make sure you follow the same path as we did for the prior 2 measurements. And my measurement is, make sure it's nice and tight, 57.9 centimeters. Let's turn the hot plate off. Put the balloon to the side, and And finally, let's work on these calculations together. So we start off with our circumference of 57.9. We are going to divide that by pi, 3.14. Once again, if you have the pi button, please use that. So we get 18.430, 14241. Let's write that in. 18.430, 14241. And that is centimeters. Now you're going to cut that in half, right? We have the diameter. To find the radius, we cut it in half. So divide by 2. We get 9.215, 071,205. That is going to be our diameter. Now to find the volume, I would immediately raise that to the third power. So if you're following along at home, that's 782.52111529 times pi. That gives us 2,458.362705 times 4. I would hit enter. Divide by 3, hit enter, and it's going to give me an answer of 3,277.81694 cubic centimeters. Once again, 3 significant figures. 7 is higher than 5, so we round to 3,280 cubic centimeters. And that's our final answer. So finally, to conclude this lab, if we look at the numbers, room temperature, we started at 56.4 centimeters for our circumference. That gave us a volume of 3,030 cubic centimeters. We took the balloon, we put it on ice, we rotated it roughly every 30 seconds. It wasn't perfect, but roughly every 30 seconds. The volume, when we decreased the temperature, the volume went down to 2,920 cubic centimeters. So now, we're about 55.7 centimeters, or roughly about 2,920 centimeters. We didn't start from our original position. We went immediately from the ice to the hot water bath, and not only did the balloon go back up to its starting circumference, but it surpassed that. So not only did it go back to 3,030 cubic centimeters, but it went beyond that to 3,280 cubic centimeters. So here, with the cold, the volume decreased, and with the hot temperature, the volume increased. Thank you for joining the Charles Love Balloon Lab. I hope you learned something today. Please join us again soon.